Hi everyone, today's lesson is mechanics. The subheading is forces and equations of motion. Now there will be 3 Newton's laws of motion, and then there will be other forces. So let's have a look. Now Newton's laws of motion, there's 3 laws there. First, Newton's first law of motion we sometimes call law of the inertia, which means the resistance to change in motion. Okay, an object at rest remains at rest, and an object in motion remains in motion with the same velocity unless acted upon by an external outside force. So there would be 2 cases, like a stationary object that it's at rest with no outside force will not move, obviously. Yes, so there's no force to apply. The object will stay just at rest. And case 2 will be with no outside force, a moving object will not stop. Yes, so like in space, you know, there's nothing to stop them, they just keep going and going, okay, constantly. Now also it says same velocity, so that means like constant velocity, so therefore your acceleration is 0 here. And also because of this, it's at rest, remains at rest, and it moving is keep moving, your net force of will be 0 as well here. So I'll remind you a little bit later. Okay, so that what happens now is greater the mass, the weight of an object, the greater its inertia, the resistance. Yeah, obviously, because the heavier the object, it's harder to move. The greater the force, it'll change its motion. Yes, so if motion is going to keep going and something is actually, you know, notching right there, and it'll move. So that's what happens. All right, so another sort of like a popular example for this first law is the person A is seated in a car with a seat belt on. The car suddenly stops and the person A moves forwards. Yeah, now you probably have that experience quite often. Yeah, I had that. And the first law says object continues in its state of motion until the seat belt stops person A. Okay, so that's what happens. All right, next one, let's have a look. Second one, it's a Newton's second law of motion. It's net force is ma, the mass and the acceleration. So acceleration, which is sort of increasing speed, happens when a force acts on a mass object. Okay, so for example, kicking a ball to the right hand side, the ball will move faster to the right hand side in the same direction as the force. Yeah, so that will happen like this. So for example, I don't know, if there's a ball here and you kicked it, that's your force, and then ball will go to here faster with acceleration in the same direction. Okay, so let's have a look at in detail of this F equals ma. Now we can use this triangle. I mean, these ones I think we quite often use for speed. STD. So if we want to know the speed, we cover the S, will be time distance, and if we want to know the times, it will be speed over distance. Yeah, and then if it's a distance, we cover the D, it'll be speed over time. So same thing happened here, FMA. So if we want to know the F formula, we cover the M, the F, so it'll be M times A. So in the between is times, up and down is the division. And if we want to know what M, in terms of M, we cover the M, it'll be F divided by A. And if we want to know the, in terms of, well, for A, acceleration, it'll be F divided by M. So that's just a little handy sort of way of rearranging the formula to work out mass and acceleration. Now, a little reminder here. So force is directly proportional to the acceleration here. Okay, so more force, more speed. Yeah, so that's linear. And this one is the inversely proportional. So acceleration is inversely proportional to mass. Okay, so the heavier, if m gets bigger, acceleration gets close to zero, wouldn't it? So the heavier the object, the less acceleration, because it's harder to move. Okay, so it's a decreasing speed. All right, so third law. Let's have a look at the third law. Third law says, for every action, there is an equal and opposite reaction. So whenever one object uses a force, let's say force 1, F1, on a second object, the second object uses an equal and opposite force, which is minus F2 on the first object. So that sort of tells you. Now, what that means, it also means M1A1 is also, minus M2A2. The forces have the same magnitude but opposite direction. Like for example, something like that. A person standing still will have, they're not moving, they're standing still. So their net force will be the same, because the force of the floor and person and the weight of the person will be same, but it's a different direction, yeah? And a book pushed against the wall is the same theory there. All right, so that's the 3 laws. Now, this time we're going to talk about types of forces. Now, this is, we have a lot of forces need to talk about before we can even start the questions. So, a force is a push or pull, any interaction on the object that will change the motion of the object, or like, you know, motion speed or the direction or anything like that. And we use Newton, capital N, for units. Okay, so first thing first is a normal force. Normal force, like trying to memorize all these symbols, because there will be a lot of forces that we have to use on the diagram for the questions to come, and you need to use all these symbols. So normal force is a perpendicular force used by surface, so it would be perpendicular to the surface. Frictional force, we use a F. Force opposite to motion, so if motion goes to the right, your friction will be to the left. Okay, and then tension force. Now tension is happening with something that is attached to rope and string or wire. Okay, most of the time it will be just one rope, one string, one wire. And applied force. Okay, applied force is the force that results when one object contacts another object or a person. So if I had this object and I apply my force this way, like that, so that's my applied force this way. Okay, or I could pull something, so that's applied force. Now, air resistance force. Now, we didn't use air resistance force when we did the projectile motion, but now we do have to think about it. So that's the R. The force that is caused by air, obviously, and it's the opposite direction because it's a resistance force. So anything is like a resistance, it's like it's not going to go with the force, isn't it? Applied force. And there is a spring force, the force used, the exerted or used by a compressed or stretched spring upon any object that is attached to it. Now this spring one is, it comes down but it will go back to where it started. Okay, so it's like sort of applies equilibrium. Okay, so let's have a look at the next one. Next force is a gravity. We sometimes called weight, it's mg. Okay, so G is a gravity, M is the mass, so it's a gravity, we sometimes call it weight. So gravitational force on an object, so like it's always going down. Okay, no matter where the force is, it's always going down. So let's have a look at a couple of cases here. So if it's on a flat surface, so basic forces will be my normal force, which is the perpendicular. If I just go down straight, it'll be perpendicular to the surface, and my gravity force down there, mg, and if this was my applied force, that would be my friction, opposite right there. So if it was on the angle, but it's still like steel motion, not moving, again, the normal force is perpendicular to the surface, and the mg is straight down. Okay, and then that's applied, and that's my friction, but it's got something to do with the angles now, and you need to form some right angle triangle to get all the forces on the object. Okay, so still and in motion objects with no outside forces, all the forces acting on the objects are in balance with each other. They all cancel each other out, yeah, because they're not moving, so there's no particular stronger force to move the object. Yeah, now there is a horizontal forces, x directions, and vertical forces, as you can see. So horizontal forces will be what? Friction and applied forces, and then vertical force will be normal and gravity force. Okay, so that's the things that we need to use. There's another one, the resolution of vector quantities. Okay, now this is what we need to find the horizontal and vertical forces. If a force makes an angle with x-axis, that's we're talking about horizontal, then force can be written in terms of components in the x and y directions. So here, if it was here, objects here, and a force was there, so it's very much like, you know, what we did in a unit circle with a trig. So if the force will have the x component and y component attached to it because of the angle. Okay, so that's what it is. Now equilibrium, if several forces act on an object and the object remains at rest, then the forces are in equilibrium, which means the net force equals 0. So if there are 3 forces in equilibrium, the forces represent the sides of a triangle. So just remember, these force forms the triangle. They're all on the same sort of direction going, so that net force is 0. So that's equilibrium on that. Okay, so remember, equilibrium is the net force equals 0. So let's have a look at the question. From the diagram, I'll just cover that, oops. From the diagram of a still object, so it's not moving, find the expression of normal force and a friction force. So that's the diagram, the given. So we need to put the friction here, okay, and the normal force here. So that was our normal force, that's our gravity. Now it should be in the middle, but I like to sketch it right to the surface, just easier for me to see the angles. Okay, so you probably would like to draw like this, and then, you know, goes the force goes to, say, friction force goes here like that. Okay, the other force will, like, maybe apply force goes like that. But I just like to use my surface as my, say, axis, like x-axis or something, so that it's just easier for me to see the angles. Now, I just want to show you, how do I know that theta is all the same here and here? So this is why. So if I sketch the normal force and the mg, the gravity force, and I just create right angle triangle there, and that's what theta, that's 90 degrees. So this angle right here, it's the 90 take away theta, obviously, by the angle sum of triangle. And same thing happens with the normal. If I draw the right angle triangle right there, this is because of right angle here. That's right angle here. So if this is 90 take away theta, that has to be theta, yeah? And then this also 90 degrees. So if this is theta, this has to be 90 minus theta. And that's a 90, so therefore this is a theta. Same thing happens with this one. So if I do that, this is right angle right there, right? So in the middle, so that has to be theta, because that is 90 minus theta from here, so that's theta. And also that part is also 90 degrees, so this has to be 90 take away theta, and that's 90, and therefore that's theta. So from now on, I'm just going to put my angles there without explaining to you too much. So what happens now is, let's have a look at this. So I'm ready for all the forces that done. Okay, so this is the object is not moving, so equilibrium is happening here. So I'm just going to have to collect the horizontal components and vertical components, so that I could actually express the forces for normal force and friction. So I just highlight my horizontal forces right there. Now I can't use this one, this is not horizontal because it's angled, so I need to create the horizontal line there with the angle on it. So this becomes my horizontal force, which is equal because it's equilibrium. And the vertical components, I just highlighted the yellow highlighter there. There's 3 of them there, because that's one here, one there, and also don't forget the gravity force there. Okay, so from here, just all algebra. So from 1, I'm gonna make in terms of f, because I need something f here in order to find the expression for n. So when I do that, because it's got cos theta and sin theta, I just want to make it into one angle, one trig ratio, which is easy to do because of either sine and cos. I can just make it into tan. So I divided by cos theta on both sides. I will get f equals n tan theta. I'm going to call it as a third equation. And then I substitute into the second, which was this. And instead of f, I'm going to put n tan theta, and then sine theta here, and n cos theta equals mg. And I'll take an n out as a common factor, and then I'll have tan theta sine theta plus cos theta equals mg. And I'm changing the tan theta into sine theta cos theta because it's a sine theta, so I could simplify. I want to make this sine cos into sort of one trig ratio. When I do that, I will get this. So when I make a common denominator, I'll get that top. That top is 1. Okay, and then if I times by cos theta, because I want n to be my subject, and I will get mg cos theta. So that's the in terms of normal force. And of course, if I substitute n equals mg cos theta into 3, which was f equals n tan theta, I'll just put f equals that mg cos theta, which was n tan theta, and I'll cancel it out. I'll get f equals mg sine theta. Okay, so that wasn't too bad. Now another one is there's a coefficient of friction. Okay, so let's have a look. There will be a point where if the angle is increased, so the angle, just using this diagram, it gets bigger and bigger and bigger, so the slope will be sharp, wouldn't it? Keep going like this. So the object will no longer be able to maintain a system in equilibrium. Okay, so that means it'll, you know, the friction work very, very hard to maintain that equal net force. So if the object is just on the point of moving just before it's sliding down, on this case, the particle is in limiting equilibrium, and the force of friction is called the limiting friction. Okay, so the magnitude, the size of the limiting friction, stays in constant ratio to the normal reaction on the object, and this constant ratio is called the coefficient of friction, mu. That's the symbol called mu. So these are the formula: F equals mu n, mu times normal force. If you want to find the mu, you could do F over n. And there are two types of coefficients of frictions, which is a static and a dynamic. Static is the both objects are not moving, whereas a dynamic is one or both objects are moving. Okay, so like a static, you know, dynamic is sort of something exciting. So question 2. An object of weight 35 newtons in rough contact with a plane inclined at theta to the horizontal is just about to slide. Just before it's moving. It means there's a friction, isn't it? And also the coefficient of friction will be there. If the static coefficient of friction between the plane and the object is this, so that's the coefficient, the static coefficient of the friction, and find the angle theta. So let's do some sketch first. Okay, sketched this. So right angle triangle, because it's about to move, yeah, and there's a normal force, and mg was the weight, is actually force, guys. That's my force. So that's mg equals 35 Newton. Okay, so that's what I've got. And friction is there. Now I put the mu n there already because there's a static coefficient of friction there already. And then it's the coefficient of this friction, which is mu. Mu is, so this is mu, equals √3. Okay, so I'm just going to, the friction is √3 normal force. And then we need to create the right angle triangles for the force, all the forces. Okay, so this triangle we haven't really talked about because we talked about this one and this one, but now we do need this as well because that's my horizontal force, that's my vertical force, because it's a right angle. So that means, now I'm just put that in there where I know that's the theta, same as this. So we know that that's a theta, and that's the 90 minus theta because that's a 90, so an angle sum of triangle, and therefore that little part has to be theta, isn't it? Because the whole thing is 90. So that's why it's a theta. Okay, so that's not too bad. And now I'll no longer put mg there, I'll just put 35 Newton. And then we just put named all the forces. Okay, so all the forces. Now these, I don't really need all of it. All I need is this and this, but I just want to show you how to find all the forces. So I'll put all the forces here. So in here, that's n, right? That's 35 Newton. That's √3n. So the angles here, so that would be n cos theta, that would be n sine theta. And in this triangle, this one is root 3 n cos. That's a root 3 n sine. And here, because it's theta is here, I will go cos 35 cos theta, because that's 35, and that's 35 sine theta. Okay, to find theta, we need to actually find the horizontal components and the vertical components. So horizontal will be easiest to find because vertical will have a little bit more. In this case it doesn't, but let's do the horizontal first. So that means this is same as this. Okay, it was just before it was moving, so we can continue with that limiting equilibrium. So that equals that, and vertical component will be n equals this. Okay, so we got this 2, so 1 and 2. Now I'm going to substitute 2 into 1 because I need n. It's in there, n, so it's a sort of like substitution. And then I'm going to make this theta into tan theta instead of a sine and cos, and that to find the theta is 60. So that wasn't too bad. Okay, next one, tension. Okay, so this video is going to be quite a long one as well. So it's a tension is something to do with a rope or wire or string, isn't it? So these are all the same rope or wire or string. Okay, so tension 1 and tension 2 on the particle D can be solved by finding horizontal and vertical components. So I just put acronym as a ST and F, so STINF. So first is a sketch, T is the right angle triangle, and name the forces and find whatever they ask. Okay, so I'm going to do a sketch now here. Sketch there, I'll just copy that. And then it was triangle, so I'm going to put right angle triangle right there. So I need to sketch it and I need to add right angle triangle here on the side. And then what do? I have to name the forces, all the forces that goes into. So that was the X, so it's alternate angle because they're parallel to each other. So that's an alternate angle here. Okay, so the angles here, angles here. So therefore my forces will be, so this one will be T1 cos X, T1 sine X, and that one will be T2 cos Y, and that will be T2 sine Y. Okay, now just remember, because it's a one rope or string, T1, tension 1 and tension 2, the forces are the same because they all have same rope. So horizontal, horizontal components is these two. T1 sine X equals T2 sine Y. And then vertical component is always like a 3 there. So that plus that force plus that. Okay. So now knowing all that, question 3, let's have a look. Calculate a tension T in a rope. So it's a one rope here. So all the same rope supporting a 10 kilograms box where the weight of the box at the center of the rope causes a to pull it down to 15 degrees, and the let gravity equals 9.8 meter per second square. So I'm going to use this STINF. So sketch. Okay, I sketch the upside down triangle, and then T is the right angle triangle, so I sketched the right angle triangle, and then N for naming all the forces, so I've done that. Okay, now this one just has the angle here, so my angle goes there because they're the same. Okay, and then I'll write it down the all the horizontal component and vertical components before I finding the tension, because that's the question says find the tension. Okay, so horizontal component, it's this, equals that. We can't really use this one because if you think about it, T1 equals T2, they're pretty much the same, so there's no force, there's just no net force. But here, there is a net force here. So T1 sine 15 plus T2 sine 15 equals 98. And we called it, you know, that T1, T2 are the same, the force, because they're one rope. So let T1 equals T2 equals T. Let's just make it as a common. And that will give us 2T sine 15 equals 98. And, oh, so the mg was, m was 10 kilograms, g was 9.8, so that's why it's 98 newtons. So we go to there, so tension will be roughly 189 newtons. Okay, so it's normally just the algebra. Okay, so let's have a look at that. Now, applied force, finally, yes. So there is a normal, the right angle, the perpendicular to the surface, and there's a gravity, the weight, the mg, and then there's applied force, so maybe it's a pulling or something. Okay, so here I'm just gonna have to create the right angle triangle and name the forces. So obviously that's applied force times sine theta, applied force times cos theta. So let's have a look. Horizontal component is that part only, but the vertical, 1, 2, 3. Yeah. Now I'll put equals mg because mg is only the going to a different direction. That is the same direction, so you add them together. It's basically, it's like this: n plus force, applied force sine theta minus mg equals 0. But we just put it into, say, mg equals those 2 plus, because it's in an equilibrium. So question 4. A 50 Newton force is applied to a 10 kilograms box at an angle of 30 degrees to the horizontal. If the dynamic coefficient of friction is 0.4, so the mu is 0.4, the m equals 10, the theta equals 30, applied force equals 50. Okay, so we got other things happening. Now I'm going to use a stimp. So this is it. I'll just sketch and then create the right angle triangle. So here we got friction happening and right angle triangle, and I just named, okay, all the forces and calculated. So let's have a look at this. This is what's going to happen right now. So the horizontal component is the only one we're going to look at. Why? Because it will only look at the horizontal direction as the vertical forces are in equilibrium. So what happens here, it says dynamic coefficient of friction, so it's just before it was moving, and it's nothing really exciting happening with the vertical, so because they're the same. Okay, so I'm just gonna do, because they're in an equilibrium, so I'm gonna go n plus 25 equals 100. I'm gonna use the vertical component to find the normal force so that I can use horizontal component. Okay, so n is 75. Therefore, my friction force is 0.4 times 75 because it's a 0.4 times n, and it's 30 newtons. So that's a 30 here. So the force, net force, we need to have a net force here, this. Okay, so that force is 13.3. So it is sort of moving the direction, positive direction, because it's 13.3. Now, net force is also MA, isn't it? Yeah. So MA, because the question says, what is it? Find the acceleration of the box. So we need to change this F into MA. So MA was 13.3 301 equals 10a, because mass was 10 kilograms. So a equals 1.33, and we'll put it in a 1 decimal place. Will be a equals 1.3 meter per second squared. So the question asks for find the acceleration of the box. The acceleration is 1.3. So it is positive acceleration in moving, so the velocity is increasing. All right, so that's the whole lesson of the forces and equations of motion. Well done.